Welcome everyone to the Ever Curious podcast. I'm Oscar Rackwell, and I'll be co-hosting this podcast with the founder of this fantastic project, Zaid Al-Shariti.
Today we're hosting Professor Barbro Melgert, a professor of immunopharmacology at the University of Groningen. Thank you for joining us, Professor.
Thank you for inviting me.
Thank you so much. It's an honor to have you here. First little adventure in the studio. And to start things off, just, I guess, introduce yourself to the audience. Just a classic question. Tell us a little bit about yourself.
All right. So I'm Barbro Melgert. I'm associate professor at the moment at the Department of Pharmacy within the Department of Molecular Pharmacology. And my background is I studied pharmacy, so I'm an actual pharmacist, but I classify myself as a respiratory immunologist because I haven't done any real pharmacy since, when did I graduate? 1994? A long time ago.
So taking this few steps back and focusing more on your secondary school interests. So how did it all start? What got you into pharmacy after finishing your secondary school education?
Well, it must be, you probably have a more active memory of that time than I have, but what I remember was that I sort of got into, in the beginning of secondary school, I was into science fiction, so I really wanted to be an astronaut. But that was a no-go basically because I was wearing glasses and women in those kinds of lines of professions were not very usual, let me put it that way. So I also liked reading a lot, so then I thought, oh, maybe I can become a librarian. But it's not very ambitious, right? So my parents stimulated for me to be a little bit more ambitious. So then I thought, yeah, what's next? So I like reading, I like detective novels, I like Agatha Christie, and I particularly like the stories about poison, so maybe I can do something with toxicology. So then it became pharmacy, and off I went to Groningen to study pharmacy.
Very
Nice.
good. Yeah. And did you ever consider working as a pharmacist?
I did, yes. Yeah. Of course, the study at that time was very much geared towards becoming a pharmacist. There was a little bit of research, but it wasn't as defined as today. So basically, everybody was going for pharmacy, and then the choice was be a community pharmacist or be a hospital pharmacist.
Yeah.
And doing the internships, I decided that community pharmacy wasn't ambitious enough for me. So I wanted to become a hospital pharmacist, but I also like doing research. So I was like, you know what, I'm just going to apply for upcoming jobs and I'll see which one I get first. So the first one I got was a research position.
Nice.
Okay,
so
fantastic.
That's me lost for hospital pharmacy.
It's very interesting actually to note that because we as students, we are mostly, we don't have a clue about what we're going to do in the future, and we think that's something that's specific to us. But it's interesting to hear that also someone like you who is an expert on their field, that also at some point was not sure of what you will be doing in the future.
Yeah, so the way I've lived my life up until now is just go with what I like, what I find interesting. Except maybe for that first step when my parents said be a little bit more ambitious.
Yeah.
But and that has worked well for me because then you're always doing something that interests you and gives you energy. But there was no plan. So, and that's okay, right? I turned out well.
Yeah,
So.
I think that's also optimistic for us.
Yeah,
That's good news for us. But was there a point, like a pivotal point, where you decided research is something for me? Research is my pursuit in life.
Well, I guess that was when you're doing your master project, and I really liked it. I really enjoyed it. I did that at the biochemistry department at here at Zurich actually, and I really enjoyed it. This just following your own curiosity, that really worked for me. So that's when I decided that it's either hospital pharmacy or research, but I'm very happy that it was research in the end, because I really enjoy it.
Yeah.
Perfect. And so, yeah, the through line after your master phase, moving into your PhD phase, was always kind of immunology, and then specifically macrophages, even when you were working on, liver-related diseases and all of that. Upon starting your research, when did this field kind of become of interest to you? And
well, that is an interesting question, right? Because when I did pharmacy, the field of immunology was not present in the studies. There was no immunology, and there was no interest. It was something very medical, because I mean, we had insulin as a protein, but the whole biologicals and drugs that are derived from the immune system wasn't there. So the first time I actually came into contact with something related to immunology was when I was doing a course at the end of my master phase, biotechnology. And we went to this company in Amsterdam called Cetus, where they produced IL-2, which was used as a cancer therapy, I think. And there we got information about T cells, and I was like, oh, this is interesting. So that's where my first little seed of immunology was planted. And then I decided that if I wanted to do research, that I would want to go that way. So then I went to the States to do an extra research project, and that was, I thought it was about immunology, but it turned out to be something completely different. But it was about trying to isolate cyclosporin. Cyclosporin is used as a drug in organ transplantations. And it was all about isolation of cyclosporin from this fungus. So it was very analytical. It wasn't any immunology in there. But I had a very fun time in the States. So.
Which is your least favorite part, analytical?
Yeah, I know. I end up with it all the time for some reason. I guess it's very important in life. That's the message, right?
So.
Seems like it, yeah, of course.
Yeah.
And then you, after you finished your master's, you applied directly to PhD position.
Yes.
And you were directly admitted to a PhD position.
Yeah, well, I did apply for several, right? I didn't get admitted to the first one I applied for, so don't get discouraged when you have to apply for a couple of positions. But I got this position, which was in liver fibrosis and trying to target drugs to specific cells in the liver to treat liver fibrosis. And that's where the immunology was further developed, because there are immune cells in the liver, and I was targeting those immune cells. But I really, really learned immunology in my postdoc, actually, when I was done with my PhD. And I went to another field, to the lung, started to study asthma, and asthma is archetypal immunology. So that's where I really had to learn stuff.
Okay.
So even when you have your PhD, you still need to learn a lot of things.
Yeah.
Yeah,
So even after a PhD, your interest was still taking form and shape. So it was not once you have done a PhD, you have found a sufficient amount of knowledge to form your future career. Because for us, a PhD is 4 years research experience when you start to dig up more and more. And it's interesting to see that it's the beginning rather than
it's definitely the beginning. Yeah.
Fantastic. And so, with this PhD thesis and everything, and where the journey has taken you via kind of the liver to and lung pathologies and working in the pathology department, and now moving into kind of general molecular pharmacology and specifically kind of focusing on the immune system. I guess this very kind of retrospective kind of look. Looking back, does it all make sense? Do all the kind of steps make sense? Would you have changed something?
You know what? conversations like this are really good for introspective looks back, right? And you start to see patterns. Like the toxicology is coming back all the time. The macrophage is coming back all the time. The analytical stuff is coming back all the time.
Yeah.
So I guess there are things that you would have wanted to have done differently. But there's nothing in my life I regret.
Yeah.
Like every step was logical at the time in my frame of mind, and it has led to a good place. So.
Fantastic.
Actually, I have a question that I know that a lot of students are asking. We as students, we have two options. We either go exploration mode, we start to explore different things, but then we lose the chance to dedicate ourselves to one thing. If you dedicate yourself to one thing early in your study, it may not be the thing that you like the most, but then you make a lot of steps ahead that you will get more chances. So what do you think, actually, looking back, is a better option?
That's a very good question, because I've always been the exploration type, right? I have a broad interest, so that has limited me in my depth. And it does hurt you sometimes, because if you're going for grant applications, you sometimes see that people who have very in-depth research line have a higher chance, because they haven't strayed from their path. They have more publications on that topic, so they have a higher chance. I also think that if you're more broad, you're more creative, and you'll be able to apply different things from different fields so the research becomes more fun, I think.
Yeah.
Because you're more open to other suggestions. Maybe.
Especially now where the multidisciplinary research and it's becoming more and more important, right?
Exactly, and I think it's important that you understand some of those fields outside your own expertise, and to be able to incorporate it all. So in answer to your question, it does hurt to be not the top expert and going in depth. But I think there's also a lot of value in being a little bit broader and being able to incorporate different concepts. So I guess it depends on your own type of interest, if you're really into one thing and really want to study that, or if you're more broadly interested.
And I assume that general collaboration skills are really valued if you are more of an exploratory type, because you have to talk with people who have the expertise, who have gone kind of mined into this topic really thoroughly. And so have you always kind of liked working in a team, kind of, or have you been more kind of to yourself, kind of working specifically on the things?
Oh, that's a good question. I guess I've always been more of a team person. But I don't mind working alone.
Yeah.
So.
What is more efficient?
Yeah. Sometimes. So there's this natural fallback strategy that people have, right? Some people immediately go seek out others when they have a problem, and some people internalize and trying to fix it by themselves. I'm more of the internalization and trying to fix it myself first. And then if it doesn't work, I go and seek out others and try to get help. And then you notice, I should have done this before. That would have saved me so much time.
Yes. I can definitely relate with that. Even in my bachelor phase, it's endless kind of experience with that.
Yeah. So and it's helpful to go through that process a couple of times, and you think, oh, wait a minute, I've been here before. I've learned something. Let's go and get help.
Perfect. So that's a nice message for anyone listening.
Yeah, I guess.
Know where your boundary is, and know when to seek for help, because you don't want to annoy people, but you also sometimes it's just totally inefficient.
Yeah, it will be counterproductive actually at some points when you're just stubborn at this point, and Exactly.
Cut your losses.
Exactly.
Perfect. So now we would like to move on to a more specific topic. And we'll start with the disease asthma. What are the characteristics of asthma, and why is it, I guess, such a big issue, and why the immune system plays such a huge role?
To start with the middle question, so asthma is an important chronic disease because it's the biggest chronic lung disease in the world. It has 300 million patients, and it's also the most important chronic disease in young people. So most young people are usually not ill, but if they are ill, they have asthma. And it's an invalidating disease, particularly for people with severe asthma. And the problem they have is that the airways are inflamed, and the airways are necessary to transport air from outside towards your air sacs. And if they are inflamed, they become narrower and it becomes more difficult to breathe. So you feel like you're suffocating. So it's not a very nice disease, especially if you're young and you want to do stuff, you do sports and you cannot breathe.
Of course.
And what was the third question again? The immunology,
Yes.
right?
Immunology, and
Yeah.
here you have an interesting point about immunological disorder.
And
Is asthma an immunological disorder?
I would say that any disorder, any disease is immunological, because any disease is a deviation from homeostasis that needs to be addressed by the immune system. But asthma is well known for being immunological because the mechanism leading to disease is very well defined, and there are also drug targets there. So in people's minds, it's an immune disease, even though any disease is immune-mediated, in my opinion.
And what does your research revolve around? Because we have seen that your research is mostly about the relation of macrophages to asthma.
Yeah.
But
Yeah. So I'm very much interested in macrophages. They have been discovered more than 200 years ago. So they've been around, right? If you compare it to other immune cells like T cells, they've only been recently discovered. So they're always hot and happening. And there you have these macrophages who've been discovered 200 years ago. And they're very prominent in the lung. There are lots of macrophages, and we don't actually know what they do. People tend to think they're there to keep bacteria and viruses out and help with immediate defense. But they do so much more. And because they have been sort of around for a long time, the interest was low. And that has led to the fact that we don't really know what they're doing in tissue. And it's not just defense of an organism against the outside world. They are also very important in getting back to homeostasis, basically, in wound repair, in all sorts of things. And we're only starting to find out how important they are. So I have a tiny little part in that discovery process of what they are capable of in the lungs. So that's what my research is about, in the context of different diseases then.
because what we have learned, I guess, at the university mostly is that macrophages are the immune cells that are capable of devouring basically the smaller bacteria and viruses and other exogenous compounds that enter the body. But you're saying now that macrophages have also a role in mediating certain signals?
Yeah, so they're not only eating bacteria and viruses, but also apoptotic cells, right? If there's damage to your tissues, then you have dead cells that need to be cleared, so that's what macrophages do. Then in the meanwhile, when they eat those apoptotic cells, they give off signals that tell other cells, okay, there's damage here that needs to be repaired, so the fibroblasts are producing extracellular matrix. In the case of epithelial cells, they need to cover the wound again. So they induce the proliferation of these epithelial cells. And these cells talk back again, right? I mean, they produce growth factors for macrophages. So there's this constant two-way communication between all these cells. But I see the macrophages as sort of the central cell in organizing all of these immune responses. And I mean, if you talk to an epithelial expert, they'll say, no, it's the epithelial cell. If you talk to a fibroblast expert, they say, no, it's a fibroblast. But in my mind, it's the
macrophages.
Yeah.
Because that also means that there are different kinds of macrophages. There's the, if I understand correctly, the M1 and M2, and I have read a research paper where they also have M2A, M2C, M2B.
Yeah, so that is a big debate in the field. So it started off with indeed M1, M2. So the M1 is the one that protects you against bacteria, etc., and the M2 is the one that repairs stuff. And that was in a similar, analogous to Th1 and Th2, because the Th1 cytokines induce M1 and the Th2 cytokines induce M2. Very nice designed principle, but too simple, of course, like anything in immunology. So what is now recognized is that there's not just a couple of 5 or 6 or whatever subtypes. There's a spectrum. So depending on what a macrophage has seen in its life, it has a certain phenotype. So that means that if a macrophage on this yellow floor gets activated by a certain cytokine, it becomes X. If it's on this black floor and it becomes activated by those same cytokines, it's slightly different.
Okay.
And it's Z. So it means that there's a lot of different types of macrophages. So we try to sort of group them into broad categories, but depending on what they've seen, they're different. So.
But are they also different in the sense that they also have different receptors and different...
Yeah, so they have different expression of receptors, different growth factors that they produce. They look different, they have a different turnover. Even if a cell that has developed in a tissue and has been in a tissue all their life and is being replaced by a monocyte that sort of starts assuming the same phenotype, it's still not the same. It might look the same, but it doesn't act the same.
Okay.
So whether the phenotype and the functional capabilities are also different. So you might have 2 cells that look the same, but they do different things. And that makes macrophage research quite difficult.
Right? It's just very chaotic, right?
Yes, and that means that all studies have different results. It's very difficult to compare stuff. And that, I think, is also why the field hasn't progressed as fast because of these issues. But now with all the new single-cell techniques that we have, it's become more easy to delineate all those different tasks.
And so talking now, we have talked about the macrophages. What is the connection between the M1 and M2 to the asthma disorder?
So asthma is the classical Th2 disease.
Okay.
So it means that certain cytokines are being produced by T cells that induce the disease of asthma. And those cytokines that are produced by Th2 cells induce M2 macrophages. So asthma is a sort of a disease that has the immune system specialized in a certain direction. And this direction is this Th2, M2, is a direction of the immune system specifically adapted to the fighting of parasites. And I hear you thinking, parasites? Asthma?
Exactly.
So somehow the immune system thinks that allergens are parasites. So
that's interesting. Is there a reason for that?
Well, the theory is that because we're not being exposed to a lot of bugs anymore, is that the immune system is sort of bored and thinks, okay, if I cannot respond to a bacterium, I'm going to respond to that. It's called the hygiene hypothesis. It's because we don't go through infections anymore and we don't get exposed to parasites, etc. Is that the immune system just doesn't have anything to do.
I'm wondering, is it because, for example, the immune system needs to be active and basically keep testing its abilities? That's why it needs to be, well, stay
Maybe.
active and try new,
Yeah.
I don't know, try.
Seems like a
Yeah.
kind of muscle that atrophies or something. If you
Exactly.
don't expose it to
If
actual...
you
that
don't
sense,
use it,
yes.
you lose
Yeah,
it.
exactly. Well,
Exactly.
exactly. Yeah.
But in this case, it overreacts and makes you remember that it's there and starts doing things that you don't want it doing. Okay, very interesting. And so, yeah, we were thinking while kind of researching, is there any ways, at least kind of on a small scale that we have looked at, where we can influence this polarization of the kind of either Th1 or Th2 responses to diseases, and obviously then whether we can alter the expression of either M1 or M2 macrophages?
Okay, sort of a roundabout answer is coming up. So there are two types of asthma, right? So most people have this allergic Th2 type of asthma, which is characterized by eosinophilia. But there's also a group of people who have severe asthma, and that is usually a more neutrophilic asthma with Th1, Th17 inflammation. So we've been investigating macrophages in this Th2 environment, and we thought, what if we now inhibit this M2 polarization? What happens? Do we then cure asthma, basically? Of course, that was our hope. So what we did is we specifically inhibited this polarization of M2 macrophages, so from neutral macrophages to M2. And then we did this in mice, and then we studied what happened to the inflammation in the lungs. And what we saw was this macrophage, because it couldn't go M2, it went M1. It's like, okay, I want to activate, I want to do something, coming back to the immune system being bored. I cannot go that way because that is blocked, then you know what, I'll go this way, and then I'll induce a neutrophilic inflammation, which means that you're actually making it worse for patients, if you were to use that in humans, because you're giving them a type of asthma which is much harder to treat and much more severe. So, okay, so back to the drawing board. We thought, this is not working. So actually you want to keep them sort of neutral, them. And the way we did that was by targeting IL-10 to these macrophages. And IL-10 is an anti-inflammatory cytokine. And by targeting that to the macrophages, we indeed could keep them more neutral, and we could keep the inflammation down. So that was the better way to go. And then that's why the research is now stuck, because there's no money at the moment for follow-up.
Okay. And sorry, I just want to retouch the M1, M2 homeostasis. So we know that M2 is more involved in cleaning up, basically, and anti-inflammatory, and M1 is more inflammatory, right? And so why do we need to inhibit M2 then, if it's anti-inflammatory?
Well, that's the thing about this spectrum, right? So there's M2 and there's M2, basically. So there's the M2 that cleans up stuff, but there's also the M2 which is inflammatory in a Th2 situation. So it's as inflammatory as M1, but it's just a different type of inflammation. And then there's M2, which is more like a repair type of macrophage.
So not all M2s are M2s.
No, no. So that's I guess the key message. Just like people, you cannot put people into little boxes saying you have this kind of people, that kind of people. Also the same with macrophages. There are many types of macrophages.
And yes, and I assume that's kind of, it's made this very complicated and very hard to research from this point. But yeah, I guess, is there anyone trying to make meaningful steps, or is just the funding not happening currently because people don't really, because it's such a broad suddenly area, people can't kind of focus in on something specifically, and suddenly the motivation just isn't there to kind of shoot in the dark and hope to kind of find something?
So the fact that this is not progressing with me is my thing, right? I just didn't get any money for this type of research lately. So of course in the world there are also people working on this. The thing with allergic asthma is that it's not perceived as very dramatic.
Okay.
So there's not a lot of effort going into finding drugs for that, because I mean we have corticosteroids, we have the beta agonists. So if there is effort, it's for the people who cannot be treated well. So that's the people with neutrophilic asthma that need different types of drugs.
Okay.
But from a research perspective in the world, there's of course still interest in how do all these cells work together and how can we manipulate them. But from a drug development point of view, there's less interest in that.
Okay.
Because it's not as
pressing of a matter, basically.
pressing. Yeah. That's the right word.
Yeah, because I also, well, this talk also got me thinking, I'm not an expert, of course, but this is just a random idea that I had, is that now we're looking at M2, one component of the immune system. It's a very reductionist approach. But I don't know, but when I learned about the immune system, it was more like the sum of the components was more than the components. So that, I don't know, is it more plausible to start with a more holistic approach, like evaluating the some of the interactions, and then maybe we could understand why different M2s are not the same.
Yes, yeah, I think that is true, because we look at all these biological processes I think too much in isolation. Just look at it, like with my experiment, right? I'm going to block M2, and off it goes to M1. So. But it's very difficult, of course, to study everything at the same time. So that's, I guess, why people are very reductionist and look at the specific process. But you always have to see it in context. And I'm not sure how to solve that. But if there are bright new minds like yourselves to solve that, I would happily cheer you along, basically. Because I think that is important, to have a more holistic view of what is happening, and also I guess in connection to the mind, because people are not just their disease, they're a person as well, and how they their makeup, not their genetic makeup, but the way they developed and behaved, and that influences disease.
Environmental factors, probably.
But also psychological factors.
Oh, psychological
right?
factors. Are we talking more placebo effect or?
Well, not just placebo effect, but also how you cope with the disease. I mean, all these factors are important, and I think they're underestimated how important these are on how these biological processes develop.
Because referring to this point. Most of cancer patients, they're always encouraged to stay strong, and I don't know. I was wondering maybe that also boosts the immune system in some way, if you have a good psychological mindset or something.
Maybe,
because it's something that's recurring. It's like stay strong. You have to.
And you know what? A lot of patients complain, but also patients with respiratory disease, but also cancer patients. The single thing that is most debilitating to them is fatigue, and we know nothing about fatigue. What is fatigue, right? I mean, it's not just a muscle thing. It's a holistic thing that makes you so tired you can't do anything, and then you want to stay strong, but if you can't move because you're so tired, then there's no way you can train. So I think that is really important to understand how that works and why that happens. Is it something, a cytokine going to your brain that makes this happen, or just like a fever, right? Something like that.
Is there any actual progress towards this kind of research, holistic research in biology and immunology?
Actually, yes.
Yeah?
So as in the respiratory field there is. We had a day with patients and clinicians and researchers a couple of years ago, and we sat together trying to figure out what the most important questions in respiratory research are, from a research perspective, from a clinician, from a patient, and all the patients came with fatigue. So that's where the fatigue came from. And then these were formulated into action points that the field needed to address. And the Dutch Lung Foundation, for instance, took these as important points for new funding. So there have been research projects into fatigue based on that. So I think that's a very nice example of how, as a patient, you can also influence research.
Okay. Yeah, very nice. And I think now moving on to the second part of the story, pivoting a little bit, that helped you kind of uncover, once again, looking at macrophages and asthma, the differences between the sexes, and especially during development. And we heard this interesting kind of, I guess, well, not anecdote, but based on obviously statistics, that boys, so in their kind of, boys between the ages maybe of 8 and up to their adolescence, more likely to develop asthma, but then they lose it once they hit puberty, or in and around when kind of the major kind of hormonal changes happen during puberty. And the opposite is true for girls or for females, is that, in childhood it's rarer, but immediately after puberty there is a higher chance, and higher rates occur at that stage. And so we would like to ask why is that, from what you've heard or from what you've obviously researched yourself?
Yeah. So I've worked a lot on that. That was another major interest, because those macrophages led me to differences between males and females, and we know that there's this switch during puberty, and it's intriguing, right? For why is this happening? And the easy answer is because sex hormones increase. So testosterone must be anti-inflammatory and estrogen must be pro-inflammatory. Problem solved. It wasn't that easy. So we did a lot of experiments there with mice. So in mice you see the same phenotype, is that the female mice get more severe disease than the male mice. So it's a very nice model to study this. So we use these mice before and after puberty to make them asthmatic, and then we also overrectomize them to make sure that there were no estrogens developing. And what we actually found was when you overrectomize before puberty, so they don't go through puberty, there's no estrogen, then we thought, asthma will get better, right? Because there's no estrogen. No, it got worse.
Wow, unexpected.
Yes.
It seems that's the story of my life. I'm very good at picking up opposite hypotheses. I start off with something and find the opposite. So we found a very nice mechanism explaining this, but that also illustrated that it's not that simple. And that's because estrogen might have a pro-inflammatory effect, but you also have the fact that these mice don't go through puberty, where a lot of immune changes happen. So these things are sort of intertwining. So we haven't figured that out yet, but the general thought is that testosterone is anti-inflammatory. There have been quite some studies that show that if you give testosterone to female mice, that they get less inflammation. And that also makes sense with the epidemiology. You see that indeed boys have a higher chance of developing asthma, but as soon as they hit puberty and the testosterone levels increase, a lot of them grow out of it. So that would suggest that it's indeed anti-inflammatory. But the role of estrogen and progesterone, we still need a lot of work on that.
So basically girls or women usually in their adult year are more susceptible to asthma.
Yes.
But isn't, I think I heard you once saying that females have a better immune system?
Yeah, so maybe that comes down to they have a better immune system, but maybe it's bored.
It's a muscle that requires more movement, more exercise.
So it could
perhaps.
be that rather the strength of the immune system is the cause of asthma, not the weakness of the immune system.
Yeah. Because in general, they're better at B cell responses, at making antibodies. And if there's nothing to make an antibody against, it's like, oh, you know what, I have this allergen here, let's make an antibody.
Yeah, exactly. So yeah, taking any exogenous kind of xenobiotic and just moving on with it.
But it's not just allergens, it's
Yeah.
also autoimmune diseases, right? You have a higher chance of developing an autoimmune disease as a female. And I think that also has something to do with the fact that, there's nothing around to respond to. So, oh, wait, something here.
Yeah.
I'm wondering, are females better at fighting cancer than males? Is there such a study?
There are lots of studies there, so I can just tell you a little bit about lung cancer. Don't ask me which specific type of lung cancer, but I know that females generally have a better prognosis but they get lung cancer more often. Also, when they're non-smokers, but they respond better to therapy. So, lots of different mechanisms intertwining again. So, depends on what you look at, basically. But so there are definitely differences.
Yeah. Would you think that there is actually a way to slow down the immune system for females so that they're, they are less susceptible to asthma?
Well, maybe we should expose girls to infections more when they're younger. I don't know. Well, there are some studies from Leiden, and it's not specific for females, but to expose children to good bacteria to protect them against the development of asthma.
What's the definition of a good bacteria?
I can't remember that specific detail, but I guess the definition of a good bacteria is a bacteria that doesn't make you really sick, because then you're not allowed to treat children, right? So think about probiotics, like the Optimal, no, what's it called? Yakult.
Yeah, Yakult. Yeah. Actimel is one of them as well, I think.
Yeah, something like that, that you can give children that you know have a high chance of developing asthma because they have a genetic background or something, and then see if that protects them against the development of asthma. So there are
plenty of fields to delve into.
Oh yeah, if you're interested in the field, there's a lot of chance to get going.
But are we good at modifying the immune system, or are we still like starting with
I think we're getting pretty good at it, especially also in cancer, right? Is with the checkpoint inhibitors that have really revolutionized, especially for lung cancer, the treatment. So I think we're very good at understanding the adaptive immune system, but I think the innate immune system is still a bit under researched and still not well understood. I mean, it's only like 20 years ago that we discovered the toll-like receptors, the DAMs and the PAMs. Yeah. T cells have been known for forever already, but we don't know these really crucial receptors for the innate immune system. So.
Yeah, and just for clarity, what's the difference between innate and adaptive?
Innate is your first response, and adaptive is the immune system that takes over from innate. When you need a little bit more specific responses. And the innate immune, it's basically innate is what you're born with, and adaptive is something that you have to develop while growing up.
And for males and females, is it the adaptive immune system that's different since they are developing that?
There's definitely differences in the adaptive immune response. So B cells and T cells are part of the adaptive immune response, and there are definitely differences there, but there are also differences in the innate immune. I mean, macrophages are different between males and females, for instance. And probably there are lots of other differences as well.
Fantastic. Well then, once again, as with all kind of research related questions, it's always more research to be done.
I guess.
It's like a hydra, you cut off one head and three suddenly spawn, so.
Can I give you a tip? If you want to go and research, please don't end your project or your report or your paper with, more research needs to be done. That is such a cliche.
Just, I guess it's the classic ending to any story nowadays for us
Yeah.
scientists. So I think
Yeah,
we should come up
it's
with
like
a more creative
scientist
way of saying it, I
Exactly.
think.
Yeah.
Fantastic.
Maybe we should ask ChatGPT.
Yes.
Give us a more creative ending to this sentence.
Are you using ChatGPT recently?
Of course.
Oh, really?
Of course.
Is it helping in your research, or what aspects of ChatGPT?
I make exam questions with ChatGPT.
Oh, wow.
Can we make the answers with ChatGPT?
But you cannot get the answers with ChatGPT. No, but also sometimes you write an abstract, but it's too long because it's only 300 words, and then I say, can you shorten this, please?
Oh, for a research paper?
Yeah.
Okay.
Or when you have to write like a bio for a conference or something.
Yes.
But the interesting thing is you do that, you say, write a bio about Barbro Melgert. It always comes back with, Barbro Melgert is a scientist, he has la la la.
Okay.
So there is a bias.
Or it recognizes your name in some strange kind of Latin way of, it ends with an O, so it doesn't end with an A, so it must be male or something. Yeah.
Something like that. I don't know,
Something
but it's so whenever you use it, check.
Good advice. I'm sure.
Yeah, but do you think would you think that it will be good to include ChatGPT for students, or that they are allowed at some point to use it, or should we always defend?
No, I think we should. I mean, there's no way we can stop it anymore, right?
Exactly,
And I think it's really useful, and it really democratizes, is that a word? The writing process, especially for non-native English speakers.
Okay.
It's so much more difficult for non-native speakers to write something, and if you can get it corrected by ChatGPT, then you have the same chance as somebody who lives in England or the US. So I think that we should use it to our advantage. Not to make it write your report for you, but to help you write your report.
That's always why I ask Oscar to check my writing.
Yeah, instead of having a friend, you can just stay at home in your own room. It's like the colleague or the friend that you can annoy at really awkward times, basically.
Okay, but from your perspective, how open is the academia to ChatGPT from what you've seen from colleagues and?
Well, the instant reaction was, of course, no, we have to prohibit it, and but
What do you call that? The caveman reaction.
Yeah.
Yeah.
So there's no way we can stop it. So we'd better teach you guys how to use it. I would say.
Exactly.
And if you're into coding. Oh, it's the most wonderful thing for coding. It's just so helpful. So.
Very good. Okay.
So we have talked about asthma, and now moving on to your next research line, microplastics. Professor, what are microplastics?
Microplastics are, by definition, pieces of plastic smaller than 5 millimeters. But that is a very wide range. That could be 100 nanometers to gigantic 5 millimeters.
And are there different sorts of microplastics?
Yeah, there are many ways to make microplastics. So they could be abrasion products from bigger pieces of plastic, or even from your clothes, right? But they could also be small by design. Think about glitters, for instance, that are just tiny little pieces of plastic that glitter and make things glamorous. But also pieces of plastic they put into personal care products like scrubs and shampoos and toothpaste, for instance. It's put in a lot of products. So that's all considered microplastic. Yeah, it's everywhere.
Okay.
Definitely.
And I know that your research also kind of fits also in the theme of sustainability. So what is the general lines in your research?
Of all my research?
Well,
of the microplastics. So the microplastics, I'm particularly interested in the health effects, and then, of course, I'm interested in lung diseases, particularly the effects on the lung, because a lot of this the attention for microplastics is directed against microplastics in the water. We all see these pictures of seas full of plastics and animals and fish filled with plastic. But a lot of people don't realize that we have as much microplastics in the air as in the water. And what is in the air we can breathe in, and that might impact your lungs. And we don't know anything about the health effects of these microplastics. So that actually is something that I want to research, and I'm actively researching at the moment.
And how do these microplastics actually come in contact or penetrate the body?
So through the lungs is one. You could also eat them or drink them.
Okay.
Or you could potentially also get them through your skin. Healthy skin is quite difficult to penetrate, but if you have a wound or you have a disease like atopic dermatitis or whatever, and when the barrier is sort of broken, it's more easy to get things into your body. But we don't actually know how much of the plastic that we find in our bodies is taken up through the lungs, through the gut, through the skin. We don't actually know how much we take up at all. So a lot of knowledge gaps there.
Yeah, and is there different sources of microplastics in terms of in-house and outside?
Well, yeah, that's interesting. So do you know what the most important source of microplastics outside is, in the outdoor air?
I assume something like, well, yeah, litter or construction would be my...
Construction is a good point.
Because a lot of, polystyrene and all the kind of foams, that they're filled with plastic,
you
I
would
assume.
think that,
Yeah.
but actually it's tires from cars.
Okay.
Wow. Didn't think of that.
Yeah.
But the second
Plenty
one,
of cars.
the second one is plastic from construction and agricultural companies. But inside it's quite different story. It's not cars, it's clothes, textiles. So synthetic stuff that we wear and use in-house.
Okay. So, but I'm just wondering now, how do you quantify the different sources of microplastics that, for
there we
example,
get to analytics again, right? Well, yeah, so, don't get me started on that. It's so difficult because you could quantify it by weight, by number, by surface area. So if you're doing experiments and you want to know if your cells respond to microplastics, do they respond to a certain amount of weight, surface area, or number of particles? Exactly. So we have to know all of these parameters and calculate them back. It's constant calculations back and forth and trying to compare experiments, because it makes a big difference. Like smaller particles have a much bigger surface area, so you think that maybe smaller particles may be less toxic or maybe more toxic, but it might be the surface area that is determining how cells respond, or it might be the weight of the... So many variables.
So we still need to correlate many factors in order to know.
Yeah, it's not just you add a drug and you you added so many micrograms per ml and then you know what it does. No, you've added so many micrograms with this surface area, with this number of particles.
Yeah, so you're trying to cover every sort of... You haven't gone with, let's just say, one way of measuring, for example, number of particles. You're trying to cover your tracks, every single kind of potential way of measuring things, and to see kind of maybe that'll elucidate what actually the reason is for all of
actually
this.
I started off with number of fibers in my case, but then I got reviewer comments, and then I thought, oh wait, I have to give them the weight as well for comparison, so the weight. And then I got into the field and I thought, oh, I should be looking at surface, and I haven't gone there yet because...
Are you required to, for example, have all of these factors and conversions in the research paper?
Yeah, sort of, but it doesn't improve readability, right? So I agree that it should be somewhere in the paper, but not in the text, because it just makes it impossible to read.
Yeah, yeah.
There'll always be supplementary
Exactly.
tables.
Exactly.
Be some appendix.
I guess that's what the appendix is for.
Okay, and moving back to, of course, the immune system. What effects have we discovered of microplastics on? We can actually start with phagocytic cells because this is the most interesting part.
Exactly.
What happens when a phagocytic cell interacts? Because we assume that the body will interact with these
Exactly.
microplastics.
So the first question is, will the body react? So we have macrophages. So we put them in a well and we added some microplastic fibers and just watch to see what would happen, right? So they could either just completely ignore it and just live their life, but they don't. So that's the beauty of these videos, right? Is that you can see, like, they're like cats. Like, oh, there's something new in this environment. What is it? And they're just looking around, like, can I eat this? And you see cells fighting over a fiber. So they're definitely not ignoring it.
Yeah.
So if they're not ignoring it, if they're actively seeking it out, that means that probably they also will respond to it, right? So the general consensus in all the papers that you see is that these particles induce oxidative stress and induce pro-inflammatory cytokine production. So we did an assay looking at 40 different types of cytokines. We thought, you know what, just let's see, because we don't know beforehand which ones we should study. So fishing expedition, let's see. So all the pro-inflammatory ones, they were not upregulated. Why? But there were 3 chemokines. Only chemokines were induced by these microplastics.
Yeah.
And in chemokines, of course, are compounds that attract other cells from the immune system. So I think what these macrophages, they see these particles and they think, wow, these are difficult to deal with. We need more help. That's my interpretation. And that's why they make these chemokines, to tell neutrophils to come and help out. But of course, it's in a dish. There are no neutrophils there, so I can't really study it. But we did an in vivo study as well. So that's where we'll hopefully see what happens to the rest of the immune system. Do we indeed get neutrophils getting in and helping out?
And then the basic conclusion is that these microplastics actually induce an inflammation.
Probably, but I don't know, because in a dish you can't. So inflammation is a process, right?
Yeah.
So you can't induce inflammation in a dish unless you add the whole immune system. So you can look at activation of cells in a dish, but not at inflammation. So I'm being a bit
Exactly.
strict here. But in vivo, you can look at inflammation, indeed. So we did the experiment, but we haven't analyzed the data yet, so I can't tell you.
I'm just
the
wondering, because
results.
like with the amount of microplastics we're exposed to, shouldn't we all have some inflammation if indeed microplastics are dangerous and they induce inflammation? Should it be like very visible and observable?
Exactly. So that's the good news, I would say, is that because it's not really observable now, it might not be that bad, but it might also be that the levels that we get, that we inhale or eat, are still very low. But the way we're producing plastic and the way we're producing microplastics is that it's accumulating. And we're not getting rid of it. So I guess now is a good time to look at those health effects and decide, do we really need to cut? What do we need to do to make things safe in the future?
Yeah.
And do you have any hypotheses of perhaps maybe certain things, and of course this is outside of I think everyone's expertise, but for example, fertility rates are dropping. That's kind of something we've been told.
Well,
and that's also something I'm questioning some of the studies, because I don't exactly know how they manage to do those, and I won't be able to speak on them. But something like that, something that we're kind of seeing. Okay, something is not wrong. Something's wrong here.
Something that is really gradually changing.
Yeah.
So you're almost not noticing it. I agree with that, but not maybe because of the particles themselves, but because of the compounds that are leaching from plastics. So plastics are mixes of lots of chemicals, and lots of additives are added to plastic to improve the properties. So there are BPA, there are phthalates, and now of course there's the PFAS problem as well that is interlinked with plastics. And these are, I think, more of a problem than the actual particles.
Okay.
Based on what I've seen, because these compounds have really profound effect at low concentrations. Okay. So there are a lot of studies out there that BPA is an endocrine disruptor, talking about male fertility and female fertility. Same for phthalates. So, and they're not regulated, right? They're just added to plastic, and it's assumed that they're not released. Yeah. But a lot of them are released. And if you get a lot of microplastics inside of you and these compounds leach from them, then that might be the way these microplastics are dangerous. But there's no data, of course, to support these claims of mine. I mean, we don't know. We know that these compounds are dangerous. We don't know how many leach from plastic. We don't know how much plastics we get, and we don't know what the particles do. So lots of don't knows.
Yes. Yeah.
Actually, talking about fertility, I also remember reading somewhere that microplastics have an effect on infants or in the development of the immune system, or was it the lung system?
It was the lung system.
Lung system.
So that's actually my own research. Is we stumbled upon. I'll be honest. This wasn't a thought out strategy. So we use a model to look at influences on lung tissue, and we use organoids for that. Organoids are like mini organs, right? And the beauty of the organoid system is that you sort of look at lung repair, which is related to lung development. And we use that system to see if something would happen when we would expose them to microplastics. And a lot of my colleagues have worked with cells and exposed these cells and look at what these cells are doing, and they're not doing that much, to be honest, if I see all the different results. But in our system, there were a lot of results. It's because we're looking at a long-term process, a repair process. And that's where we saw that the development of airways, of the repair of airways, is strongly inhibited by certain plastics. And then not by the particles themselves, but compounds leaching from them. So that's why I was talking about all this.
Oh, so it's not the microplastic itself?
It's not the microplastic itself, it's something which leaches from it. And we cannot find what it is. So we did analysis.
Is there a lot of them
analytical analysis? We looked at what is leaching from plastic, but all the things that were leaching at high concentrations, those didn't have any effects. So there's something leaching in a very low concentration that we cannot pick up with normal methods. So we have to find some other methods now. So it's present in very low concentration and has a huge effect. That's scary. I mean, that is the definition of a toxin, right? It's very potent in a very low concentration. So that appears to be happening to the development of lungs.
And actually, do we know if these compounds have the ability to cross the placenta? And it's more dangerous, right?
Yes. So the microplastics have actually been found in placentas. So yes.
Not good news.
No, exactly. So that's where all the organ systems develop, right? So if you have a lot of microplastics there with compounds leaching from them, but it's all about dose. So we first need to know how much are we exposed to, how much actually gets inside, and then how much of that tiny little bit that we cannot pick up is leaching from it.
Exactly.
So we need better analytical methods. I can't believe I'm saying this. We need better toxicologists.
Yes. There we go.
Yeah, because everything is toxic at a certain dose.
Exactly. Yeah.
And of course, that's where collaboration comes in.
Yeah. Yeah, because analytical methods is not my forte.
Exactly. So there we go. We need more people, mass spec geniuses
yes.
working out some really
High
really-
resolution mass
yeah,
spec. If
yeah.
anybody knows how to do that,
Yes.
please let
Well,
me know.
there's
I
the
need that.
Orbitrap mass spec.
Yeah.
Did you hear of it?
I've heard the term. I have no idea what it
Yeah,
means.
me neither, but I just know that it's high tech.
Yes.
Everybody is talking in awe about, we have an Orbitrap.
Yeah.
Okay.
Yes. Only a select few of people can actually explain what it is.
Yeah.
Yeah. So
100%.
maybe that should be the next person you invite to
Yeah,
talk.
maybe.
Yeah, yeah, truly. Fantastic. And just a short, maybe few words on what you're excited to pursue in the future.
analytical
Maybe
chemistry,
what's
maybe?
something that's looming on the horizon that
Well,
that is appearing.
yeah.
be
So
super
so
interesting.
research-wise, and I'm looking for that compound, right? That is leaching. And I was reading this book. It's also made into a movie. It's called Dark Water. And it's about the PFAS scandal in the United States, where DuPont was polluting an area around Parkersville, West Virginia, because they were releasing PFAS into the environment. And they were releasing it on the land of a certain farmer, and he saw his cattle slowly dying, and he got lung problems and health problems, etc. So it describes the journey of this farmer trying to take on DuPont to get, to get them to stop polluting, basically, and a lawyer who helps him in this process, and it took 20 years or something. So there's a lot of PFAS discussion in Holland as well, right, about the toxic effects of PFAS, etc. And I was reading this book, and I was thinking about my leachate. I was thinking, oh, this guy had lung problems. So I thought, if it's so potent in very low concentration, could it be leaching from my microplastics? Could this be the mystery compound? So and we were using nylon particles. So I started investigating, are PFAS used in the production of nylon? Yes. So that is my exciting new horizon. Is I was getting into this because of this microplastic and the leaching compound. But then I also got a broader vista. It's like, but PFAS really are a big problem because they're released in endless quantities in the environment, and they're so potent in very low concentrations. It's scary to think about that we're polluting ourselves. So a level of 1 ppb is already toxic. If that is in the environment, you're in trouble, basically. The levels in the Waddenzee are 8 ppb. So 8 times that level.
8 times the toxic concentration.
Yes.
Wow, and nobody is doing anything about it.
And nobody's. So that got me excited is the wrong word, right? It got me worried, and when I'm worried, I want to do something about it. So actually, I thought we need more research on this topic.
So the research is not definitive at this stage that it's toxic, or is it definitive that?
It's definitive that it's toxic, but how it really works? There's so many of these chemicals, and there's not that much on what happens to the lung. So I thought, you know what? Let's research that. So.
Sometimes when I hear how much toxic things are in there, I just feel that it's a miracle that we're surviving.
Yeah, exactly.
Well, that's a good news, right? I mean, we don't just die like that. I mean, we've developed in this world. We can handle some stuff, but I mean, this is something we can prevent. We don't need to put that out into the environment. We just need to tell companies to don't put it out there.
Yeah, exactly. And yeah, in relation to that, any recommendations for just day-to-day life and for the person to avoid or
Microplastics?
decrease their susceptibility to microplastics? If, once again, if we find that there's a very, very dangerous link of the leaking
better safe than sorry.
substances. Exactly.
Yeah, better, but that accounts for all types of air pollution, right? If we just keep it to the lungs for this topic, is just keep your exposures as low as possible. I know a bonfire is nice, but it's really polluting. And try to keep the air quality in your surrounding as good as possible. So indoor, ventilate, make sure it's not too dusty. Outdoor, don't go with a car anywhere, just use your bike. Just be aware that they haven't found any lower level of toxicity for air pollution, right? So the levels that are now the WHO standards, that's not the level at which they didn't find any problems. It's still at that level you find influence on lung function.
Yeah.
So try to avoid exposing yourself, but have fun too.
Yes. So ventilate, everybody.
And ventilate. That's always good.
Keep the windows open if it's not too cold. Fantastic.
I think
that is it. I think
we reached the end of our conversation. Thank you for this informative conversation. We really had a good time conversing with you.
I had fun too. Thank you very much for the invitation.
Thank you.
Thank you. Thank you.